of recording. Okay. And on the left, we have a select and a project. So the project is happening in the SQL select statements select portion. So again, a SQL select statement is comprised of 3 parts. Even though I'm writing them on different lines, it is one statement. There is a select, from, and a where. The select is doing the project portion, the pie portion of relational algebra. The from we will be getting a little bit more into today, and the where is what is doing the work of the sigma. So the sigma in relational algebra is a select statement. Again, don't confuse the select in relational algebra with a select in SQL. Although they're the same words, they're very different mechanisms behind each. And the where statement is where most of the conceptual work goes into, trying to actually filter out the results. So here on the left, actually I'll focus here on the bottom one. These 2 select statements on the left return the same type of output, but the second table is, or the second SQL select statement, I'm renaming the table as something else. This is another thing that I want to enforce in this course. Again, it doesn't have an appreciable output or an appreciable effect on the output of the statement, but it helps avoid conceptual mistakes. So especially when you're referencing the same table or you're referencing many, many tables, renaming them can make these things more clear. So again, the last lecture we started to discuss taking relational algebra queries and turning them into SQL queries. And I was giving some requirements about how to frame these queries using the SQL select grammar. So far, we've discussed a simple select on the right and a select in addition to a project, which is on the left. So without further ado, let's continue with going from relational algebra into SQL. Let's see. All right. Let me copy these. Odd. Sorry, my keyboard seems not to be working. That's not great. So just you have them in your mind, I'm going to be pasting these tables again, and So up here, we have a select statement and how to realize it in SQL. Here we have a select and a project taken together and how to realize it in SQL. Now we're talking about another primitive, which is the cross product. And I would like to know how you would realize this cross product given the SQL. Let's make that R1. I'll give you a minute to think about it. And please write your answer if you have one. So how to write this in SQL? That's my question. Okay, so I'm still seeing silence in the chat room. I'm going to be sharing a clock. I'll be giving you guys an extra 2 minutes. Again, my question is how to realize the cross product. So we have tables R1, S1, and I'm asking how to realize the cross product in SQL. So I'll start this 2-minute timer and give you guys time to think about it. If you have some answer to it, please put it in the chat. I'll come back after the timer's done. How's baby doing?
Oh, you still teaching?
Yeah.
I don't want you to write something for me.
I have a minute.
Just 1 minute?
Just 1 minute. Literally.
Okay. Just write really fast.
Okay.
I talked with this guy in a Gchat, so according to our conversation in Gchat, through Gchat, hi Bobby, I just write from here.
Yep.
You cannot what I say.
Okay.
Yeah. Hi Bobby. It was according to our conversations through Gchat. Use your language. Okay, mine is not correct. I will ignore the campaign. Blah blah blah. I will fix it. Okay.
Mhm.
Blah, blah, blah.
Okay.
I will gonna campaign. I don't know how to say. Okay. I will gonna campaign and campaign as they have exist segments 100, 105 and 138. I don't know how to use that word. Like 分别. There are two campaign here, there's two number, like 分 for them. You know what I mean? 分别.
Mm-hmm.
I don't know how to use that word.
Non-overlapping.
Not so complicated.
Different? Separate.
Not separate. So that I really good campaign. This campaign has this number. This campaign has this number.
Existing.
As they have existing segments.
Segments. Sorry.
Segments.
105 and 138, respectively.
Oh yeah, means like, right? Separate. So respectively. Is there existing segments?
Respectively, so this means this one corresponds to this one corresponds to that.
Yeah.
Sorry, I gotta get back to lecture. Mm-hmm. Sorry, baby. Yeah. Okay, let's see. I'll take these in order. From R1 as R, S1 as S, where R equals S. So I see this statement. Okay, I will reiterate. A SQL statement is composed of three parts: select, from, and where. For now, take each of these as being a required part of the SQL select statement. So a SQL select statement is comprised of three elements: a select, and a from, and a where. So this answer is missing the select. Also, where R equals S, I'm not sure how to interpret that. So the where portion of a SQL statement is what's called a predicate. That's applied to every single row of a table. A predicate is a statement that evaluates to true or false, just like the relational algebra select statement. There's a relation, which is a schema and an instance, and the select in relational algebra is a predicate that is applied to every single tuple of the relation, of the instance of the relation. And anything that passes the predicate, that is to say, any tuple of the instance that evaluates to true, given the predicate, is kept, and anything that evaluates to false is thrown out. And that's the way that a relational algebra select statement works. So here, R and S are tables, and I'm not sure how to interpret the R equals S. R would be a table, S would also be a table, and I guess here is trying to see if these two tables are identical. Doesn't quite work. I hope that's clear. If you have more questions about it, ask in the chat. In the meantime, I will move on to other answers that I see. Select R1 times S1 from R1 is R, S1 is S. First of all, thank you for renaming tables, the both of you. Create table. So the create table is something that corresponds to the creation of the table initially. This is something that corresponds more to when we were discussing ER diagrams. And ER diagrams, let's go back. ER diagrams are made up of entities that are connected to other entities through some kind of relationship. Entities can have attributes, and there are participation constraints that connect entities to relationships. ER diagrams do not have an instance. What I mean by that is that when you go from... So ER diagrams are comprised of these parts of a vocabulary: entities, relationships, attributes, keyed attributes, and participation constraints. That's it. That's everything that's in an ER diagram. In a relation is comprised of a schema and an instance. The schema are the names of the attributes, their types, as well as the instance, which are the values of, or the rows, if you like, of this type of table. The ER diagram only captures the schema. And even then, it only captures the named attributes portion of the schema. It doesn't really capture the types. The types are something that are added to a relation. When you are defining an ER diagram or defining a relation that realizes an ER diagram, you're only talking about the schema portion of it. And when you're defining the schema, this is where you have the create table stuff. So the create table, this is really only talking about the schema, the top part of the table, the names and the types, and the keys. So that is how you set up the tables that you're working with. Wow. I'm sorry. Our cat just came in here. Leave it, I guess. So.
Just have class.
Okay, I'll handle it. Thanks. Okay. So the create table part, this is just realizing the schema portion of a relation. Insert, delete, drop, alter, these parts are how you put information into the table, how you put a row into the table with an insert, how you delete a row from the table, how you delete a table in its entirety, and how you modify a table, which is adding a column or deleting a column. What we're talking about now is this select, the query part of the table. So all this stuff up here for the relations, these are kind of the quote-unquote easier things. What do you want the table to look like? What's the schema? And how do you insert, delete? What we're focused on at this part of the course is the select. And as you saw from before, I just wrote the word select. But this is really the hard part of SQL, when you're trying to actually query information. So this select statement, which here I just wrote as select, actually this is select something from something where something. So from last lecture, including this lecture and our next lecture, are just focused on this part, the query. Given a set of tables, how do you extract information from them? So this create table here, this would have happened much earlier. This is separate than the select statement. Again, if you have, oh, can I increase the font size? Yes. As I'm going through these, for the students who are proffering these examples, or any other student who has questions about them, please ask in the chat as I'm going. I see this. Third try. From R1 is R, from S is S. Similar to the first attempt here, this is only a part of the select statement. So a select statement in SQL has 3 parts to it. Even though I'm writing them on different lines, it's a single operation. There's a select, a from, and a where. I'm writing them on different lines just because, but all of them taken together are what comprise a SQL statement. So you, at the very least, yeah, you should have a select and a where from this. Brian, let's see. 4th attempt. This is getting much closer. Oh, much closer. Select RID, RBID. Okay, a couple nice things. First of all, this. So I'm going to try to rearrange these so I can have things captured on the same screen. So here on the left, attempt 1, attempt 2, attempt 3, and now here, attempt 4. So here we have select r.sid, rbid, rday, and sid, sname, srating, sage. So he's not using a star. Excellent. That's what I'm asking to do in this course. Thank you. And the from here. R1 is R, S1 as S. This is correct. This works. There is something that I will get to, but there is no where here. But I'll get to that.
Professor?
Yes.
So why would you need a where in this situation if when you're asking for a cross product, doesn't that just produce every possible combination of the 2 tables? And it's not like it's asking for a natural join, which is where you would have to use a where statement, right?
That's right. So again, you're correct. What I want is to try to explain what's actually happening with the SQL language. So,
oh, okay.
This is why I'm not sort of before when I was talking here about having a distinct, and you can write a star here instead, or you can also explicitly write things out. This is not only to emphasize what's actually happening, but also realistically, this is something that will catch mistakes in the business world when you do it this way. Here, renaming a table, that also avoids conceptual mistakes and is something a little bit different, but still. But as we're here, I'll go ahead and touch on this now. So a select statement is comprised of a select, a from, and a where. I've said that now a few times. So now my question is, here, this is correct. In SQL, you write this, you will get the cross product. Why does this return the cross product? Okay. Socks before shoes, as they say. So a SQL statement has a where portion to it. What the designers of SQL decided was here, as Brian correctly points out, there's no filter here. So the cross product is taking all possible pairings between table R1 and table S1. So the result of this should be all of these pairs taking every row of S1 and gluing it together with the first row of R1 and taking the second row of R1 and gluing it together with every row of S1. Then this sort of mega table will have these attributes from R1, SID, bid, day, and these attributes from S1, SID, sname, rating, age. And that's captured here in the select. We want all of it. So for this very first line, this is going to output 22, 101, 10, 10, 96, 12, Dustin, 7, 45. That's this very first line, gluing the first row of R1 with the first row of S1. And once they're glued together, we want everything from this table. And that is this. This is saying everything. 7 attributes. 3 from the first table, 4 from the second table. Which tables are being used in this operation? R1 and S1. So here we have R1, we're renaming it. We have S1, we're renaming it. And the where is the select, the relational algebra portion of the select. But here we're not filtering anything. We want everything back. So how, if you have a where, assuming that it needs to be there, how could you have a where such that nothing is filtered out? You want to keep everything in this table. The where here is predicate equals true or predicate equals false. You're kind of onto something. So the where is where you have a predicate. Yeah, you state predicates in the where. A predicate is a statement that evaluates to either true or false. This predicate is applied to every single row of the table. If it's true, the row is kept. If it's false, the row is deleted. And whatever passes is output as the result. Have one of each connected by an or. I'm not sure what one of each is. And you'd also need to specify what the predicate is.
Professor,
Yeah.
could you do something where like you take into account where SID, like where R1.SID equals S1.SID, but also take into account when they don't equal each other? You know what I mean?
Yes, that's one way. Sure. So what he's saying is R.SID equals S.SID. But this is filtering out things because, for example, here, the second row, here R1 SID is 22, but S1.SID is 31. So that would not pass this predicate test and would be thrown out. But we want to keep it because we're asking here to do a cross product. So he's saying R.SID, this is how you write a not equals S.SID. This not equals, you can either write it this way, using a less than greater than sign, or you can also write it this way. Where either way you choose, I'll leave it like this for now. Where R.SID equals S.SID or R.SID does not equal S.SID. This is something that we'll always evaluate to be true. Yes, Tashar, you're saying basically the same thing. Yeah, just there's the exclamation point equals or the bang equals is not the vocabulary of SQL. I just covered that, but yes, that's one way to do it. You cannot use the bang equals. That's not in the SQL vocabulary. So the way to write this in SQL, you can do it this way, or not, whatever. Let me make this bigger. So you're familiar with Python. In Python, you write not equals this way. In SQL, you can write it this way using the less than greater than. Otherwise, you can write it this way with a not in front and then whatever it is that you're negating, making it equal. That's the way to do it in SQL. So this works. This is a predicate that always evaluates to being true. You could also do, for example, R.SID equals R.SID. Does something equal itself? That's something else that always evaluates to true. Or anything else that you can think of, any predicate that evaluates to true. You can also do this, where true. Just the word true is a predicate. It always evaluates to true. But because this was proffered here, maybe that makes sense to everybody, so I'll keep it like this. The designers of SQL decided that you can take a select statement like this and see if I can get this all fitting on one screen. the designers of SQL decided that these two should be equivalent. Although a select statement is comprised of three parts, a SQL select statement has a select and a from and a where. In the case that the where statement is a predicate that always evaluates to being true, in that case, it can be omitted. And the omission of it should be understood by users of SQL that the predicate is something that always evaluates to being true. So what Brian wrote is correct. He wrote it just here on the right. These evaluate to the same thing, but again, just so you understand the way that SQL is actually working and what the designers of SQL, the choices that they made, these two things are equivalent. So this is correct. For this class, you can write it either way. This is something I don't care about, but I thought I should spend some time actually explaining it. Okay, because I'm not seeing questions about it, I will move on to the, is it okay that we don't use distinct here because all the cross products in this case are already unique? Good question. Really, I would have liked to see distinct here. It's true that implicitly these will all be distinct from one another, but better to include it. Because there's no reason that we would want to see repeats. It's true that implicitly you will not see repeats. Having the distinct word is what I would prefer for this class. Thank you, Eric. Good question. Okay. Now, there's another part that I want to emphasize here. This from. R1 is R and S1 is S. So this is a select, a SQL select statement that's being applied to a table. Which table is this select being applied to? So here, you're choosing, this is a projection. This is the select, the relational algebra select, taking a predicate, applying it to every single row of a table. What is happening here? R1 is R, S1 is S. The combined table. What is a combined table? I agree, it's a combined table, but combined in what sense? After the cross product. Not quite following. You call on both tables. The fields from both tables are combined into one big table. Yeah. Right. So I think Jamie basically gets this. We are not calling on both tables here. So here we have a table R1 that already exists. Separately, we have a table S1 that exists somewhere in the database. Now we're doing a select statement. Here, the select distinct, this is doing a projection. That is, this is choosing which rows, or which columns, excuse me, of the table to output. The where, this is a predicate that works on a single table, where for every row of that table individually, this predicate is applied. If the row passes the predicate, if the predicate evaluates to true on this row, the row is put into the output. If the row evaluates to false, it's not put in the output. The from is under the hood doing a lot of work. So conceptually, the where is where the most of the work is done by people putting together the query. The from is where under the hood, SQL is doing a lot of work. So we have a table R1 with some values, whatever, SID, sailor ID, and other stuff. We have a table S1 that itself has an SID, some other stuff. What this from is doing is for each table that's referenced. So here we're referencing table R1 and we're renaming it R. And we have table S1 that we're naming S. The from is creating a table R cross S, where here we have R.SID and stuff S.SID stuff. So this from takes every single table that's referenced in the from statement, and it performs a cross product, and it creates one large mega table. It's one big table, just one table, not many tables, one table. And it does a cross product and a rename. So here, this SID is renamed to R.SID. This SID is renamed to S.SID. And every attribute of the R table is preceded by the R. So here, this would also have R.bid, R.day, where here you have SID, bid, and day, and the S table has name, rating, age. Each of these get preceded by whatever you named the table here. So S.name, S.rating, S.age. Okay. So this from is doing two things. It creates a very large table that is the cross product. And this cross product, again, is every possible pairing. With two tables, if here this table has length 2, this table has length 4, then there will be 8 entries in this table. If you had from R1 as R, from S1 as S1, S2 as S2, for example, then it would be 2 times 4 times 4, or 32 rows to this very large mega table. So everything that's happening inside of this statement, the from creates a single table. Could be a very large table, because cross products are all possible pairings. If you're referencing many, many, many tables, you're doing every single possible pairing of all of the tables. It's also renaming each of the fields, each of the columns of this table, because as in this example, each of the tables might have the same named attribute. Table R1 has an SID, table S1 also has an SID, so to disambiguate them, this large mega table is also renaming, each of the columns to make them unique. Then the where statement in this large mega table is applied to every single row, and anything that passes the predicate is put in the output, or the candidate output. Anything that doesn't pass the predicate is not put in the candidate output. And then the select takes the candidate output and only focuses on those columns that you want to output. And that's it. So that's everything that's happening with a SQL select statement. There's 3 parts to it, and that's everything that's happening, including kind of under the hood. So the from, this is something that the writer of the query doesn't have to think about so much, but this is what's actually happening underneath the hood. There's a very large table that's being created. For the SQL query writer, the where statement is the part that's really important. Once you've decided all of the different tables that are relevant to this query, you can throw all of them into the from. But given this potentially very large mega table, which rows should you be keeping and which ones should you be striking out? That for the SQL designer is the hard part. This actual select, this is a super easy part. This is just what do you want to output? Like which columns do you care about from this very large mega table? Here, because I'm asking for the cross product, we care about all of them. So this is the cross product table. This cross product table, this mega table, is being created implicitly because of this from. And whether or not you have a where statement or not, if you don't have it, it's implied that the predicate that you have is always going to evaluate to be true. You can write any predicate if you like that does always evaluate to be true. This is one example. So it should be s.sid. And that's it. Any questions about this? No. Okay. then I think there's already, let me see if I can copy these, just because. I think there's already students who are jumping ahead to this, but how to do the natural join between R1 and S1 in SQL. I'll remind you that the natural join is taking two tables, and if they share a common attribute, in the case that these two attributes equal each other, then the row is kept. You can realize the natural join without needing it, really, by doing a select and a project and a cross product. I guess I'll give you guys 2 minutes to work on this. Okay, sorry, for the sake of time, I'm already seeing people putting answers here. So, yeah. I think if people have got it, basically. So, just take this. So here we're doing the cross product and a project. And what we care about is the select, where r.sid equals s.sid. So just to make this a little bit explicit, taking the cross product of these two tables, we would end up with, I'm sorry, I'm not getting all this to fit on one screen. I'm taking R1, this table, and the cross product here, S1. And so there's assuming that we're taking the cross product of these two tables, now the natural join is looking at these SIDs and seeing if they match. So here in the first row, see if I can get things to... This from here is what is doing this stuff. So this is the cross product. The result of this from is this large mega table. Now we're focused on the where statement. This is a predicate that's applied to every row. So here, yes, let me rename this A and B. Just to make it match. Okay. So this from is doing a cross product and a renaming. And now this where is looking at each row. This row gets eliminated, this row gets eliminated, this row gets eliminated, this row gets eliminated, and this row matches each of these. So the output will be all of the contents of these two rows. A.sid, this column, A.bid, A.day, B.sid, B.sname, B.rating, B.age. Okay, so the output will be 22.101, 10.10.96, 22, Dustin, 7.45, and this row. Okay, copy this. So speaking of these predicates, here, the where. What type of predicates are allowed? Again, a predicate is, oh, do you need both A.sid and B.sid? Either way, I mean, technically the natural join would remove one of them. Yeah, so you could remove one of these because they're equal by definition of a natural join. So yeah, technically the natural join would choose one of them and delete them. Yeah. So here, in a where statement, again, a predicate is a statement that evaluates to either true or false. So what types of predicates are allowed here? Okay, and or. There's more than just that. Let's see if we can make a comprehensive list. And or not. Yep. We've already seen more than this. There we go. Equals. Not equals. I guess I'll do that this way. I'll add it. Not equals. Greater than, less than, greater than, equal to, less than, equal to. There's some more. No is. No between. I mean, between, you can realize this with a less than, equal to, greater than, equal to, and. null. Still, that's equal to null, not equal to null. Basic arithmetic. So you can multiply, you can divide, you can add, you can subtract. Sure, true, false. Yes, aren't this true, false? Yeah, so this is it. So you could do something like a.sid plus 1 equals b.sid and a.sname less than 10, whatever. You can combine statements like this. So here you can do basic arithmetic to values. This is doing an equality. This is using an and to take two truth statements and put them together, referencing a different field and comparing if it's less than something, whatever. Okay. The next one. Here it's the union. Yeah, I mean, I'd like to give people time to think about it and stuff, but given where we're at the semester, I guess I'll just go through this a bit more. So here we have the two relations, R1 and S1. Select distinct. So here we're projecting, and so we just care about the SID. There's two tables that are relevant. There's the R1 table and the S1 table. So we're putting them both in the from. The where we just want everything, and there exists this union statement. Sorry. Okay. So the first part of the statement, we want the SIDs from table R1. That's what this is doing. So we're taking the R1 table and we're projecting just the SIDs from it. With that, separately, for this, there's a select. So we're referencing table S1. That's this from. We're renaming it. We are eliminating those columns where the age is less than 48. That's what this where is doing. we're only keeping those entries where the age is greater than 48. And from this table, we're only keeping the SIDs. Then we're taking the union between the two. Similarly, if we have the same thing, but instead of a union, an intersection, SQL also supports this, intersect. For the same reasoning as above. And I will leave you with this. Minus the set difference is realized with except. Same reasoning as above as far as getting this left-hand side, getting this right-hand side. The minus here is with the word except. What I will leave you with is that this except is not supported in MySQL. SQL, the language, supports it. MySQL, which is the free version of SQL that you might use, doesn't have the word except. That being said, you can still realize this query without it. You can think about that over the weekend, and I'll pick it up here from the next lecture. But so far, in relational algebra, we have the select. We've discussed how to realize this in SQL. We have a project. We've discussed this, how to get this in SQL. The select in relational algebra is realized in the where. The project is realized in the select portion of a SQL statement. We have the cross product. This is realized in the from, which is really what the from is doing under the hood. Renaming, this is also done in the from statement, where you rename columns. The natural join, which by itself, actually you don't even need, and you can realize it through other operations, but that is a simple extension of the cross product, where you just add that two attributes should be equal. And then there's the union, intersection, and set difference. That's the vocabulary of relational algebra, each of which are encompassed by the SQL select statement. So the SQL select is actually more powerful than the relational algebra, because everything that relational algebra can do, SQL select statements can also do, and more. But yeah, this is the way to go from one to the other. Next Tuesday, reading day. No, next Tuesday is going to be a class. Yeah, I wanted to make it a reading day originally, but I apologize, I'm running a little bit behind, and there's still some SQL stuff that I want to cover. So next Tuesday will be a class, but I will be holding office hours next Thursday. Absolutely, and if students for some reason want extra office hours, I would be happy to hold those on Tuesday as well, but please let me know in advance if you would like that. Monday's the last day of classes. Okay. Sure. Then the final will only cover everything up till now. That's it. On Tuesday, I will still hold class. If you want to learn a little bit more about SQL, it will be optional. There's some SQL things that I haven't covered, mainly joining and group by, some SQL stuff. I will be in class. If you would like to follow along, it is optional. It's not required. Everything that will be on the final will include everything up until today, and no more. Okay, so that's it. Thank you, everybody. I will post this lecture on YouTube as well as this slide to Blackboard. Is the intersect different than the join? Yes, an intersection is different than a join. So a join, first of all, there's different types of joins. What we've discussed in this class is the natural join. There's also a left join, right join, inner join, outer join, but really they're all just variations on sort of the same thing. And in fact, you can even avoid using a join altogether. You can realize it through other primitives. An intersection would be so a join is realized with I guess it depends on if we're talking about SQL or in relational algebra. In relational algebra, it's realized with a cross product and a renaming and a select. And this is the main reason why the intersection is different than a join, because you have to have a cross product. If you were to, well, yeah, I don't know what else to say about it. You have to have a cross product in order to see if the values are the same in one table versus another. So an intersection doesn't quite do that. All right, thanks everybody.